Good morning, ladies. It is Tuesday, March the 31st. It's payday for me, anyway. And in the last week and a half, I very well feel like I've earned that, but it has been a whirlwind. I just want you to know that. Okay, so today we're continuing on with probability. And I think everybody has taken their quiz. If you do have questions, you're always welcome to reach out. Abigail, I do have your answer to the question that you had for me the other night in the Zoom meeting. So just let me know when you want that. And we can Zoom and I can show you what we did. Okay, so today we want to do 9.2. And 9.2 talks about multi-stage experiments, okay? So in 9.1, we talked about one-stage experiments. So what's the probability of getting a heads? What's the probability of getting a 6 on a die? What's the probability of drawing one card? So it's a one-stage experiment. So you're just working with one draw, one roll, one flip, okay? One spin of the spinner. So today we want to look at a multi-stage experiment and how you figure out the probability for that. So a multi-stage experiment is you roll a dice 3 times, and what's the probability you get 2 6s and a 3? So you work that. Flipping a coin 5 times, drawing a card 2 times, what's the likelihood of 2 aces? So multi-stage means you're doing whatever activity you're doing multiple times. So you have to put all of those probabilities together. So before, in our one-stage experiments, we added probability. So what's the probability? So we added those together. Now, when we look at multi-stage probability, a couple of ways to look at it. So first example, one-step problem. You're given 3 red marbles, 2 yellow, and 5 blue. So what we did in the last section is the probability of a red is getting 3 out of 10. So we have 3 options to get a red out of one draw. It does not specify whether you're pulling out 3 marbles or whether you're just multiply your probability of getting a red one. So 3 out of 10. Now, if we change that to a multi-step problem, then what we end up having is the probability of getting 2 yellow. 2 yellow. So there's 2 ways that we can look at this, the tree diagram and the multiplication principle, and I've showed both of those for you. So your tree diagram is you start out and your first draw, you either get a yellow or not a yellow. A yellow, let me put my cursor on it, a yellow or not a yellow. So your probability of getting a yellow is 2 out of 10. Your probability of getting not a yellow is 8 out of 10. Now, we're doing this without replacement, and that means we're not putting whatever marble we choose on the first time back in the bag. So our second time we get a yellow, we can either, after we get a yellow, we can get another yellow, or we can not get a yellow. So from there, if we got a yellow the first time, our probability of getting a second yellow is 1/9. Our probability of not getting a yellow is 8/9, because there's still 8 in there that are not yellow. So you can kind of see those. So if we didn't get a yellow the first time, we still have the option of getting a yellow the second time or not getting a yellow the second time. So I kind of wrote it out here. The line above means not. So yellow, 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 not yellow, not yellow, yellow, and not yellow, not yellow. So this is the one we're looking for. We're looking for the probability of 2 yellow. And so the multiplication property is the probability of 2 yellow without replacement is the first time we have a 2 out of 10 chance of getting a yellow. If we get a yellow on the first time, then we only have a 1 in 9 chance of getting a yellow on the second try. Okay, so without replacement. So if it was replacement, you would put the first yellow back in, the second yellow, and so you still have a 2 in 10 option, and we'll see an example with that. So it's 0.0222 probability that you'll pick out 2 yellows. Okay, so here's another one. You still have your 3 red, 2 yellow, and 5 blue. So what's the probability of pulling 3 marbles of the same color Well, 3 marbles of the same color. So our probability, we can get 3 reds. So we want the probability of 3 reds. Plus we want the probability of 3 blue. 3 blue, because we can get 3 blue. Now, the reason that yellow is not included here is because there's only 2 yellow marbles. So the probability of getting 3 yellow marbles is 0. That's not possible. Okay, so we want to add those 2 probabilities together. And again, this is without replacement. So the probability of 3 reds, so you have a 3 out of 10, and then 2 out of 9, and 1 out of 8, so each time getting a red, plus the probability of 3 blues, 5 out of 10, 4 out of 9, 3 out of 8. So then we want to add those 2 probabilities together, and so we have a 0.0917 chance of getting 3 marbles of the same color. Whoops, I'm pushing buttons here. I want to do that. Okay. Now, a note about replacement without replacement. So without replacement, the probability changes from without replacement. So if you don't put it back in, the probability changes from stage to stage. And that's what we see right up here. From reds, we see it goes from 3 out of 10 to 2 out of 9. So that probability changes from stage 1 to stage 2 to stage 3. Now, some cases require replacement. So draw 3 marbles with replacement if it says with replacement. But we also have options where replacement is not even an option. You can't flip a coin and take out heads after you've already got heads. Okay, it's either heads or tails. You can't spin the spinner and take out one of the colors. So sometimes there are places where replacement is not an option. You automatically get replacement. Now, if your sample size is large enough, then with the replacement and without replacement will not. The probability will be similar, so it's not going to affect anything. So now we can talk about statistical independence. Statistical independence, and this is where the outcome of one event has no influence on the probability of the second event. Okay, so this is where we talk about the flipping the coin. Heads, it will always be 0.5 probability you'll get heads, 0.5 probability you'll get tails. There's no option there. Okay, the same way with the spinner. It's always going to be what it's set. So those have no outcomes. So when you are statistically independent, then you multiply your probabilities together. Multiply your probabilities together. So statistically independent. So here's the case. So you roll the dice twice. We're still doing a multi-stage experiment, but in this case, our probability doesn't change. Event A is event of a 6 on the first roll. Event B is the event of 6 on the second roll. The first roll, if you get a 6, the probability is 1/6. The second roll, probability of B is 1/6. They stay the same. So the probability does not affect each other because you can't take away those options once they're there. So your probability of rolling event A intersecting with event B. So basically this means rolling a 6 on the first roll and a 6 on the second roll. So you multiply together those probabilities. So event A intersecting with event B. So 0.0278. Okay, the next one, if we flip a coin 10 times, if you flip a coin 10 times, the probability of heads on the first shot is 1/2. The probability of heads on the second, the third, the fourth, the fifth, all the way up to the probability of heads on the 10th is still 1/2. All of those stay the same. The probability of heads on the third flip after first 2 heads, it's still 1/2. Okay, and that means that it's independent, statistically independent. So I didn't write this, but if you were wanting to find the probability to flip the coin 10 times, then you would multiply 1/2 times itself 10 times. And that would be your probability to get heads 10 times in a row. Okay, so the second one, an example where we do draw 2 cards with or without replacement. So with replacement, what's the probability of drawing an ace of hearts? Okay, so if we're replacing this, so the first time we can get, there's 1 try out of 52 cards to get an ace of hearts. Okay, now with replacement means I'm going to stick that card back into the deck, and I again have 1 out of 52 to try to get that. So that's where this probability stays the same. So this is when it's considered independent. Now, without replacement, this is where it becomes dependent. The second stage is dependent on what you get in the first one. So without replacement, the probability of getting an ace of hearts. Well, if I pull an ace of hearts the first time, it's 1 out of 52. And don't put it back into the deck. So the second stage of getting an ace of hearts, well, there's only 1 in the deck, so that means I don't have any chance of getting, so 0 out of 51. 51. So the bottom number changes because I didn't replace that card. But again, there's no chance there. So that's where, so dependent statistics means they depend on the roll before them, okay? Or they depend on drawing the card before them, the stage before it. Independent means it doesn't matter what happened the first time. You have a new system the second time, okay? Again, make sure you are looking at some homework, trying some of these problems. I did post a week at a glance for this week. I'm going to try to do that to kind of show you what's up and coming to maybe prepare yourself a little bit more and be able to get some things done. So today 9.2. Thursday we'll do 9.3, and then I'll also open up a quiz over 9.2, 9.3 in my math lab. So that will be for Thursday, but all that information is under the Blackboard announcements. So if you have any questions, let me know. Otherwise, happy probability.